Hello friends, welcome to another tutorial in network analysis and synthesis. In this tutorial we'll also solve a network using 5 different techniques, and we'll compare those techniques, which technique turns out to be the easiest and which technique turns out to be the lengthiest. And we've taken up a network which is a little tougher than the network that we took in the previous video. So the first technique that we wish to apply is the superposition theorem. In superposition theorem, we find the current in the required branch taking one source at a time, and we wish to find the current in 10 ohm resistor branch. So this is what we will find in all the 5 cases. Now we have 3 active sources, 1 voltage source and 2 current sources. So we'll need to solve this network thrice to find the current in this branch, and then we'll add those currents depending upon the direction of the currents. When we take 20 volts voltage source, the network reduces to this form. When we take 20 ampere current source, the network reduces to this form. And when we take 5 ampere current source, the network reduces to this form. And please understand, we've simplified the network by joining these 2 resistances in parallel to just one resistance, because we are concerned about this 10 ohm resistance. So we are simplifying the network to an extent where it becomes easier to calculate the current here. So in the first case, we know that the total voltage is 20. The total resistance faced by this 20 volt voltage source is of course this 2 is in series with this voltage source, and these 2 branches are parallel. The first parallel branch consists of 10 ohm resistor, and the second parallel branch consists of 16 ohm resistance. So the total resistance is 8.15. The total current out of this 20 volt voltage source will be 2.45, and when 2.45 ampere current appears here at this node, we can simply apply current division rule, which is total current entering the node into opposite branches resistance upon opposite branches resistance plus my own resistance. I get 0.94 ampere of current in this branch of 10 ohm resistance. And next we take up this case, because this is much easier. We simply wish to find I triple dash, and that can be found by current division. Total current entering this node is 5 ampere into opposite branches resistance is 7.67 upon opposite plus my own resistance gives me 2.170 in the downwards direction. Now when we get to the third network, we need to further reduce this network resistors into 1. So I get 1.67, 10 parallel 2 gives me 1.67. So 20 ampere current when enters this node has 2 branches where it can go. Either it can go into 5 ohm resistor branch, or it can go into this 12.67 ohm resistor branch. We are concerned about this branch, so 20 ampere current. So the current through this is labeled as I double dash, or this is I double dash, I'm sorry. So that comes out to be 5.67, and we know that the total current in this branch will be the algebraic sum of all the currents, 5.65 minus 2.170 minus 0.94. So that comes out to be 2.54 amperes in the upward direction. So that is the answer that we get. Total current is 2.54 using superposition. Now next we take up mesh analysis. In mesh analysis we can clearly see that there are 4 meshes, and I've labeled the current I1, I2, I3 and I4 there. And by inspection you can see that the loop current here I2 is equivalent to minus 20 amperes because the direction of this current is opposite to that of the loop current, and I4 by inspection turns out to be minus 5 ampere, and the direction of the loop current is opposite to the independent branches current. And in loop 1 it is pretty easy. So this is 20 volts. So we start our journey from here. We go from positive to negative. So it's a minus 20 plus 2 into I3 minus I1, and then we again go from negative to positive. So a plus sign, and 10 I1 is the voltage drop across this resistor. That turns out to be equivalent to 0. And in this loop we have 1, 2, 3, 4 and 5 elements where the voltages are dropped. So the voltage drop at 1 ohm resistor is I3. Voltage drop across 2 ohm is minus 2 I3 minus I1, and this is 20 volts, and then minus 5 I3 minus I2 minus 10 I3 minus I4. And we know that the value of I2 is already minus 20 and I4 is minus 5, so we can simply put minus 20 and minus 5 here. And from the first and second equation we can find I1 and I3, and the current in this branch will be I3 minus I4. So by solving equation number 1 and 2, we get I1 to be equivalent to 4.39, which we're not concerned about. I3 is minus 7.575, and we are concerned about finding the branch current. So it will be I3 minus I4. So the current through 10 ohm resistor will be I3 minus I4, and that will be minus 7.575 minus 5 because I4 is minus 5. So we get minus 2.57, and the supposed direction was downwards because I3 loop current is going downwards, and the negative sign shows that this is moving. The actual current in the branch is moving upwards, so which is in sync with the previous result. Although we got 2.54 ampere in the previous one, but that is acceptable, I guess. Now we proceed on to the third one, which is nodal analysis. Now our network of 3 sources and 5 passive elements can be redrawn like this. I always like to redraw the network like this because it clearly states 3 nodes A, B and C, and the currents also look very easy at the nodes. So what we can see is that at node 1, I1 current is entering and I2 and I3 are leaving. So at node 1 the Kirchhoff's current law will give me this equation. At node B, we know that I2 is entering, I3 is entering, 20 ampere also is entering the node, and I4 is the only current which is leaving. At node C, 5 ampere current is entering, I4 is also entering, 20 is leaving, and I5 is also leaving. And by the way, we are concerned about finding I5. When we express all these currents in terms of voltage upon resistance, we get, because the direction of the current is always from higher potential to lower potential, so we consider 0 minus VA upon resistance is 1, then VA minus VB upon 10 is I3. This is, by the way, I3, and VA plus 20 minus VB upon 2 is I2. So we get this equation. And similarly at node B, I2 is this, I3 is this, and 20 is also entering node B, and what is leaving is I4, which can be expressed as VB minus VC upon 5 ohm resistance. And at node C, we know that 5 ampere current is entering, then I4 is also entering, which is VB minus VC upon 5, and what's leaving is 20 amperes, and this is also leaving. So VC minus 0 upon 10, which is equivalent to VC upon 10. So from these three node equations, we get three equations with three variables, and we can find VA, VB, and VC using 991 ES calculator. So we get VA is equal to 7.54, VB is equal to 36.79, and VC is minus 25.47. We're concerned about VC because I5 current can be found using VC upon 10. So I5, which is the current flowing through the 10 ohm resistor branch, is VC upon 10, which is minus 25.47 upon 10, gives me minus 2.54. This minus sign shows that the direction of current is the opposite to what we presumed. All right, now we go on to the next theorem, which is Thevenin's theorem. In Thevenin's theorem, what we do is we reduce our circuit into a simpler network of one voltage source and its equivalent resistance, and then we connect the load in series to those two elements. So we are concerned about finding the internal resistance of the network RTH and the open source voltage at the load. So in order to calculate RTH, we remove all the voltage sources and current sources. We short circuit the voltage sources and open circuit the current sources, and we find the resistance as seen from the load. So when we do that, the network reduces to this format. And further simplifying this network, because we need to see the resistance from these two open terminals, so we have 5 in series with 1.67 in series with 1. So the total Thevenin's equivalent resistance turns out to be 7.67 ohms. In order to calculate VTH, we open circuit the load and we calculated the open circuit voltage at the load. Now this becomes a little trickier, because in order to find this voltage, we'll need to apply some technique which already has been applied. By that I mean that in order to find this voltage, I'm applying KCL again, because at this node I can clearly see that because 5 ampere current is flowing in this branch, so I can see that the total voltage here is 5 volts. So at this point A, the voltage is V, and at this point B, the voltage is VOC, which we are trying to find. So at node A, we can say that V minus this voltage upon 10, because let me assume this current to be going outside, and then we have V minus 20 minus the voltage at 1 ohm resistor upon 2. So let this also be the outgoing current, and what I have here is V minus VOC. This is also outgoing upon 5, of course, and which is equivalent to 20, which is incoming. So at node A, 3 currents are moving outwards and 1 is moving inwards. And at node B, there's a slight mistake here, because 1 current is moving, because we have assumed this current to be moving in this direction, so this must be a negative sign here. So if we get a negative sign here, we get a minus 45 volt here by solving 1 and 2. Please understand that V minus VOC upon 5 is also leaving, also entering the node, and 5 is also entering the node, and 20 is leaving the node. So a slight mistake here, so you should correct that, and solving 1 and 2, you'll get VOC to be equivalent to 45. Once we get VOC and RTH, we can reduce this circuit to its Thevenin's equivalent format. So VTH is 45, RTH is calculated. We connect the load back again to this circuit, and we get the load current to be equivalent to 45, which is total voltage upon the total resistance, which is 10 plus 7.67 in this case in series, we get 2.54 amperes of current flowing, and that too in the same direction that we have found so far. So far we've been consistent in finding the answers. Let's go on to find the answer by using the Nortons Theorem. In Nortons Theorem, the first step is the same as that of the Thevenin's theorem. The internal resistance or the equivalent resistance or the Norton equivalent resistance will be calculated in the same way we calculated RTH, but in this case we need to find the current source value, which is the Norton equivalent current, and that is found using short circuiting the load. Our load was connected here, the 10 ohm resistor was connected here, so we short circuit that load, and now we are trying to find this current IN. So again, as you can see, in order to find IN, I'll need to apply one more technique which already has been applied. I'll use KVL here in this loop, and then I4 is, let us say, known to us, and then IN will be equivalent to I3 minus I4. In order to get this Norton equivalent current, we'll need to apply KCL again within the problem, so that makes it lengthy. If we were to apply KCL, then we could have applied it directly also. Anyhow, but we need to solve it using Norton's theorem, so we take up 4 loops, and by inspection I2 is minus 20 ampere as mentioned in the KCL process, and I4 is minus 5 ampere. Finding I1 and I3 will not be difficult now, because the equation for loop 1 will become 20 volts and the voltage drop at 2, voltage drop at 10 equivalent to 0, and over here voltage drop at 1, voltage drop at 2, voltage drop or the voltage source itself, and then voltage drop at 5. So the only term which is missing is this 10 ohm resistor voltage drop. So over here in loop 3 we just have 4 elements, so we get this equation. From these 2 equations we can easily get I1 and I3, because the value of I2 is already put equivalent to 20 here. Solving 1 and 2, we get I1 to be equivalent to 5.38 and I3 to be equivalent to 11.53. But the Norton's equivalent current is, as I mentioned, is I3 minus I4, so it will be minus 11.53 plus 5, so it turns out to be 6.53. So we've gotten our current source, and when we draw Norton's equivalent circuit, we place a current source of this value, and the minus sign just indicates that the direction of the current is opposite, and R internal is also calculated in the previous case, 7.67, load resistance is 10. Simple current division, 6.53 current entering this node will get divided into 2. I'm concerned about finding the load current, which will be total current entering the load into opposite branches resistance upon opposite branches resistance plus my own resistance, which gives me minus 2.83 ampere. This answer is a little different from the ones that we've gotten other techniques, but I guess it is still acceptable. But let me know in the comment section about what do you feel about this change in this solution for Norton's theorem. And I hope you liked this video. This is again a comparison of all the techniques that will illustrate which technique is beneficial, which is not, and which is quicker, which is lengthier. And if you liked the video, give it a thumbs up. Consider subscribing to my channel. Thank you for watching the video. You have a great day ahead and a good life. Bye.